Yes.
Oh, thank you. Okay, so it's my pleasure to present the paper, Seismic Performance of Corroded Reinforced Concrete Columns. Yeah, let me put it back there where it was. Using accelerated bridge construction. Now, most of you know, of course, about corrosion, and you know about accelerated bridge construction, but we don't know very much about seismic performance of these columns. First, let me introduce my research assistant, graduate PhD student, Sayal Shrestha, who's my student on this project. And the contents of the paper is the ABC and its advantages, the corrosion effects in ABC and other reinforced concrete construction, the details of the specimens, which unfortunately were delayed due to the COVID-19, but I actually have some good news and some pictures to show you at the end of this presentation. We finally were able to cast the concrete. And a few things about accelerated corrosion and how we will proceed with this corrosion. And then in the early morning session, you remember Xian Ming presented that not only are we going to do experiments, but we need prediction models for corrosion. So here we have a very special model that we're working on with OpenSeas, which is an open source code for earthquake engineering and seismic performance of structures, which we actually, since we couldn't do the experiments, we tried to see if we can model these effects of corrosion on the seismic performance. Then I'll show you some of these results of pure simulation, conclusions, references, and as I said, a little bit of where this is going and our progress in the experimental campaign. So as you've heard from our keynote speaker, Dr. Kalegi, ABC has advantages, accelerated bridge construction. A major one, of course, is fast project delivery. But of course, our hope is that one of the other advantages will be improved durability. And durability, of course, here in terms of corrosion. So again, ABC can provide less interruption to traffic, especially in urban areas, higher safety, we hope, and better quality control. And the last one is for sure, because all this concrete can be actually precast, pre-manufactured in the precast yard. So actually there should be very little that's left to chance. As you know, constructing in the field can involve quite a bit more variability. So ABC, I'm showing here something to introduce people who are not familiar to ABC. This is a study we completed some time ago with one of my former students, MJ Ameli, on accelerated construction of bridges using prefabricated elements and components. So here you can see we used a grouted duct, actually a grouted sleeve. It's called a splice sleeve, but it's still a connector. You prefabricate the column, you prefabricate the footing, and the same thing with the cap beam, and you connect them with these grouted sleeves. So this is all the concrete is already pre-manufactured, and in the field you would only have to grout, as you can see here, with an inlet and outlet. So the quality is very good because you've already done your manufacturing in the precast yard. So the concrete is very good quality. The details are very good. There is very little that can go wrong in this construction method. Of course, the question is, what is the seismic performance of these pre-manufactured elements? And the answer, of course, is well known, and it's pretty good. So that then the next question is, well, how do we know what the durability of these components are going to be in the field? So that brings us to the corrosion, and you've heard a lot of presentations today about corrosion. In this respect, though, for bridges, we're mostly interested in what's the reduction due to corrosion in terms of load carrying capacity. Mainly the effects we're worried about is cracking, of course, of concrete and loss of bond strength. And then reduction in the yield strength of the reinforcement, this could happen, and the loss in confinement. And of course, after that, you will see that, I'll show you some pictures from previous work. You will have cracking and loss of area of the rebar. That's a major one. So here is some pictures that show corrosion effects in the concrete, reinforced concrete. This is just a simple column, a short column. And you can see the effects on the left on the steel spiral, and you can see buckling of the vertical bars and even some fracture of the steel spiral. On the right, you can see in the first picture here, A, you can see there is nothing there because this is our control. And the second picture, though, shows that corrosion has a major effect. In fact, you can't even find where the spiral continues here. And again, buckling of the vertical bars. This was because these columns were tested in compression after they were corroded. So you can see buckling is a very prominent feature. And again, the loss of the spiral is a serious issue here. This was work done by my student, Mike Gibbons, and my colleague, Larry Rivley. And it can definitely show that corrosion effects are major. In this particular study, we had about 15% loss of the vertical steel area and about 25% of the spiral, wherever you can find it, of course. And the result was we had about a 25% axial load reduction in the capacity of these columns. This shows you what happens after 11 weeks of accelerated corrosion. This method here was the Florida DOT method with 5% solution of salt by weight. So it's a tremendous reduction in capacity in this particular case due to gravity load. But of course, our interest in this project is seismic load. So we ended up constructing 4 specimens, and I will show you the dimensions in a little bit. One of those will be a control specimen. One of those will have a moderately corroded condition. In this case, we assume that this is 30% loss in reinforcement area. And one will be severely corroded with 50% loss in reinforcement area. And the fourth one will be identical to the third one, but it will be corroded and then reinforced with carbon fiber reinforced polymers. Those of you attending the session this morning with Alex Dado, you know what I'm talking about. We're going to try and retrofit it after it's corroded. So these are the geometric details of the specimens. A major difference and departure from the previous study with MJ Amelli, we decided to use a 3-inch galvanized duct instead of using the NMB splice sleeves. You can see we have, in this particular case, 8 bars. These bars are going to be then grouted in the footing, as you can see here. And in addition to being grouted, the grout that we will use is a grout we actually developed here, which is very high strength concrete. We can develop about 11,000 PSI, which is a very good strength. Our concrete is typically 5,000 to 6,000 PSI. So these grouted ducts work very well. We actually use them in a current project for another project, and they are doing very well. The bars are 8 number 7, and we have the spiral number 4 at 2 inches. And in addition, we're actually debonding these bars to get better seismic performance, because the seismic performance, we will apply a lateral load up here on the top, going back forth to the left and to the right. And so we debonded the bars 8 inches in the column and 4 inches in the footing to improve the strain characteristics of these bars at the interface. So as you can see, the columns are 16-inch octagonal. They are about 8 feet tall. and the footings are 2 feet high, 6 feet long, and 3 feet in the y direction into the paper. So you can see the cross section here of the column into the footing, and here you can see the cross section of the column in the free area. And in the top we have a square section which is 16 inches deep, so we can apply the lateral load. So this is the details of the specimens. So as I said, in the accelerated corrosion, we plan to use the Florida DOT method with a constant current. Typically here we use Faraday's law to calculate the steel loss. And as I mentioned, we were shooting for 30 to 50% loss in area. So, and then we can calculate actually what the steel loss over time is as well. So how we plan to do this, we plan to build a box, if you will, with a high density polyethylene and metal cathodes. We already have wires that are embedded in the reinforcement, the vertical column reinforcement to the anode. And then we start with the battery to initiate this accelerated corrosion. And again, we'll use 5% salt from the local area. That's what they use on the bridges here in Utah. They put a lot of salt, and we plan to get the salt from them to start the corrosion of the 3 columns. So in the meantime, though, since due to COVID, our lab was closed, we developed some models based on OpenSys, which is an open source code for seismic design. And we use force-based beam column elements with 2 nodes for each column. Concrete was modeled with using a model concrete 4, and reinforcement was modeled using reinforcing steel. So we use a plastic integration method to predict the cyclic behavior of these columns. And we assume a plastic hinge length of 8 inches. This was based on previous research that I showed you earlier with my former student Amelie. And we took an axial load applied to the top of the column vertically, equal to about 6 to 10% of the axial capacity of the column, roughly about 100 kip. So this picture here shows the OpenSys model. As you can see, there is only 2 nodes actually, and the top node is actually the one that's being displaced to the left and to the right to get the action, the cyclic curves of force versus displacement. You can see here there are 2 sections. We have section 1, which is going to be away from the corroded area, which has the original reinforcing bars, the unconfined concrete, and the confined concrete. And then section 2, where we have the corrosion, we have in the area where we have the grout, we have a pseudo reinforcing bar with a confined concrete and unconfined concrete. And as I mentioned, a plastic hinge length of 8 inches. So in order to use the model, we defined the Manders model for confined concrete. And many of you are familiar with it. It actually provides the effect of confinement of those steel spirals on the confining concrete strength capacity, both for axial force, axial stress, and axial strain in the column. So this is a very sophisticated model. And the reason we chose it, of course, is that it can represent even the case where the bars start corroding, as I will show you in just a minute. And so this shows, for example, the stress strain curve for unconfined concrete. That's the orange line. And then when you confine it with steel spirals, it shows it in the blue line. So in the OpenSys model, we need to also model the bond slip in the plastic hinge zone. And here we have Dr. Tazarf. We are using his model with Professor Saidi from Nevada, Reno. This uses a modified strain to include the bond slip using these expressions that you see here that Professor Tazarf, I'm assuming, developed during his PhD, which links actually the bond of the bars, the strain in the bar, and the bond forces with bond slip. And this is incorporated into our model using bar slip springs. So here you can see the stress strain curves for the reinforcement. You can see the orange curve is the original reinforcement. And then you can see the blue curve, which includes the effect of bond slip. The orange curve was the model developed by Haber, and then the blue one is developed by Professor Tezar. In addition to bond slip, though, in cyclic motions for earthquake, we need to model the low cycle fatigue because that's how eventually the bars fracture. So we use the Coffey-Mansion model with Kuna's cumulative linear damage rule, which is shown in these expressions, which has to do, of course, with the strain that you can apply, the level of strain, and the number of half cycles to failure. Some of the constants here were changed to alter the behavior of the reinforcing steel based on a model by Mazzoni et al. And there is actually a command CM fatigue, which was used in the OpenSys model based on Dakal and Maekawa to model the low cycle fatigue. In addition, as I showed you in the pictures, it's possible that some of the bars will buckle. So in order to include buckling of the longitudinal reinforcement, we use a model developed by Gomez and Appleton. And this model is also included with this command GABAC in OpenSys based on the Gomez and Appleton model. So in the OpenSys model, we need to model the corrosion. So corrosion, we try to model it at least until this point by changing the mechanical property of the reinforcing steel. And there is a paper by Yuan et al., which proposes actually that based on the corrosion level, you can reduce both the yield and ultimate strength of the steel bars. You can also reduce the elongation, and you can also reduce the ultimate strain. So from these four expressions, actually, we parametrically included here reductions in the area of the longitudinal steel bar by 30 and 50%. And this corresponds to the two specimens we're going to corrode for 30 and 50% moderate and severely corroded specimens. And the area of the spiral, we're reducing by about 50% for both corroded specimens. We found that if you don't reduce the area by 50%, you're unlikely to achieve any considerable reduction in the effect of the spiral. So here are some preliminary results before we did the test. These are predictions. You can see the cyclic load displacement curve. The vertical axis is the force, horizontal is the displacement. And you can see the model goes all the way up to approximately 8% drift ratio. That's the horizontal movement of the column divided by its length, or approximately 8 inches in this case. And you can see actually we achieve fracture of the bar at about a drift of 6%. Here are the results for a moderately corroded specimen. That's the one on the left with the green line. You can see as compared to the blue line, which is the control specimen, we're able to achieve fracture again. But as you can see, the curves are severely reduced here. The area under the curves, which represents the hysteretic energy during the earthquake, is severely smaller. And you can see that, again, we achieve bar fracture due to low cycle fatigue. The one on the right has 50% corrosion. And you can see the red curve is much lower than the blue. In fact, it's lower than the green if you can compare between the two figures. And that's what we expect. We expect that 50% corrosion will be more severe than 30% corrosion. The same thing is here shown in the hysteretic energy, which you can see the blue line is the control specimen. It achieves very large hysteretic energy. The green, which is 30% corrosion, much less, and the red 50% lower than that as well. So preliminary conclusions, we see significant loss in lateral force capacity for the corroded specimen compared to the control, about 35% to 50% for the severe. And loss in hysteretic energy is about 43% for the moderate and 58% for the severe. And we also see some reduction in lateral displacement capacity, but this is not very conclusive yet. I think we will see that when we do the experiments, and then we will calibrate our models. So I want to acknowledge Try to Relief for the financial support, Sika USA for the composite materials, and Geneva Rock for the concrete. And as I promised you, these are the references in the paper that I'm presenting here. And in the ongoing research, we actually, just last week, we were able to cast the 4 columns and the 4 footings. And here you can see the corrugated ducts, which are in the footing. And here you can see the bar extensions, which will actually be grouted in these footings, as I mentioned earlier, when we make the specimens. And finally, we plan to, of course, one of the specimens we will retrofit with carbon fiber. And this is some picture that we have done this in the past, and we know how to retrofit the corroded columns. And this shows you how we plan to do the 4th specimen. So, and that's the end of my presentation. Thank you for your attention. I will take any questions.
Thank you so much, Dr. Pantelis. Very interesting study. I see one question by Dr. Shi. He's asking how to incorporate into your model the fact that rebar corrosion is non-uniform inside the concrete.
Yeah, that's an excellent question, Xianming. I have thought about it, and I think what we're going to do, we already started doing it. We will slice the column into finite strips. So when we actually, in the experiment, after the test, we will take out the concrete and we will measure the bars and cut them and observe them first. And then we can slice the column into finite layers, let's say 1 inch thick. And then each one of those layers, we will actually model in our OpenSys. We know how to do it. We've already started doing that. Different severities based on a map of what the situation is of the steel inside, both the vertical steel and, more importantly, the spiral, because the spiral is the one that's going to create the reduction in the capacity. So we will slice the column into 1 inch thick slices, for example, in the model. I don't know if that answers the question. I don't see Xianming talking, but I guess that's my answer.
Yeah, I just want to raise the awareness like this.
I do not see other question, but I want to mention this. I'm personally very excited about this study because I believe that's the first study seeing the ABC technology with corrosion.
Yes,
and that's like
right.
excellent work, excellent thought, and let me congratulate you. And I'm very excited to see the result of it.
Sure.
So we are assuming that ABC is behind the scene, is kind of hidden. So they should perform the same as cast in place, but there is no proof for it. So that would be the first one. And the field application are fairly new, less than 10 years. So we really do not have a lot of data to compare the long-term performance of these structural detailing.
Thank you. Thank you very much.